Alrighty, so right now we're gonna go through these two pages, and how we're doing it is the hard way because they just give us a summary. They don't give us how they got it here, which is this whole entire process, which involves the Lagrange polynomials and a bunch of other stuff. But here's the secret: after a while, you realize that analytically you can only get it for hydrogen. Otherwise, the other molecules are too complex and need numerics later on. And secondary, I don't understand the point of doing all that to get these results. I think you could just use these results and understand the assumptions made and then just do it. That's what you should do. But for me, I'm a person that needs to know the reasoning behind something for me to actually be able to use it. So instead of going to like 16 different articles, finding this stuff, I asked chat and it got a horrible answer at first, but after feeding it more my thinking, it got into the right direction, kind of. And then eventually I just said, okay, whatever. It got somewhere, and it's kind of how it works. So the first thing we'll do is start over here with the classical orbital mechanics is where my brain directly go. So this is orbital mechanics, this is energy, this is P over 2m, and then this is potential. So like in orbital mechanics, there's potential and then there's kinetic. And how you can see that is if you plug in mv into the momentum over here, mv squared and 2m, that's 1/2 mv squared, right? So ching there. Beautiful. And then you see that the potential is just gravity or electrons or whatever it could possibly be. All right. So that's beautiful. And funny enough, this is kind of where we're going to begin. All right, so we start over here with these two constants over here, which is the Planck's constant that we're using. And with our wave distribution, the wave square will be the probability density for finding the particle near the location x and blah, blah, t. Now, we start over here with this. Basically, we're gonna use the total energy, so we're gonna try to plug everything into there. So we start with our assumption of being sine and cosine because it is waves after all, and those are sines and cosines at the end of the day. And then we try to figure everything out. And clearly, yeah. So we need a bunch of other things, but first off, we need to define these two as our definitions for now. Those are going to be P equal Planck with a dash, which is basically divided by 2 pi, and then omega, and then no K, and then energy will be H multiplied by omega. And then over here you see a derivative for here, and then that equals this form, which is the classic form, and you multiply that over here, which gives you this kind of thing. But you know this is P, right? So you can say that this over here is basically P, which gives you this. And if you extend it to 3D, you get a gradient, basically. And why is a gradient instead of like the other forms is because if you think about it, it's a gradient because it's a vector still. So we need a vector to get everything correctly. So over here is what we get. We do the same process over here with energy, with derivative in time, and you got this form over here, which is this, and you see this over here is E by definition, so we get this form, and we plug it back to this equation, which gets you this final form over here, which is a complicated form in the X direction, but we're going to change it to a gradient form later on. Yeah, that's a little confusing, but that's what happened. I'm going a little fast because there's no real point for you to know this later on. I just need you guys to know that there is a way to get this thing, and that's there. And finally, yeah. So from here, we are doing this. We're getting this form over here as last time. And then what did I do? Oh yeah, here we're doing internal. So uh basically we're gonna see later on there's gonna be external and internal again, but we're gonna focus on the internal for now. And here we're gonna use what we did in Dr. Becker's class, basically, 210C fluid mechanics, just to get this form over here. We'll just assume this solution over here. And with this assumption, we get this factor over here when you plug this into here. And this simplifies to this form over here, which is H theta equal E phi, sorry, phi. They just multiply each other, which is quite useful. But this is a Hamiltonian operator. If you want to know more about that, go ahead. You can have fun with yourself. Um, we go over here and we do what we learned in Rosegreen's class, Dr. Rosegreen. This will be orbital mechanics, how to shift your masses to get into this form over here. So this is the same thing we do in orbital mechanics over here. So we get RE on RP just by manipulating the center of mass. So this, in the case over here, is the velocity of the whole system. If I were to analogize myself into orbital mechanics, what we're doing is basically we have this, right? Instead, well, let's make it a little bit more interesting and say orbital mechanics like this, and it's moving this way, the velocity total. The velocity is moving that way, and that is the velocity over here. This little velocity is the tiny velocities over here, is kind of what's happening in orbital mechanics, and that's kind of what's happening right now. And you see that the V that's kind of what's happening. Yeah, that's kind of the vibe that's kind of understanding you have over here. Well, yeah. Yeah. So not quite true, but it is true. I mean, over here you see R minus RC, so it's a little different. So it's like this, but you have RC and the distance between the point over here vector, and you're getting the distance R, so it's going to be for that case, it'll be the same thing. So imagine maybe three of them, and then you have a different total velocity versus like the independent, like minus each other velocity. It's kind of what happened, but it's a little confusing. I remember doing it in Doctor 240, and that's basically what happened. It's orbital mechanics, basically. At the end of the day, something that is true, you have this format over here, um, which is not that bad, and with that said, we can plug into our energy equation over here. And this energy equation is, our classical 1/2 mv square. And in this case, because we're using hydrogen over here, we're going to have the same electrons Q over here. So we attach this thing to the total energy, which is the potential energy, as you can see. Now, when we plug into here, we get this form. And you see over here, these two cancel out basically, because, yeah, they do cancel out. And then these two over here, you add it, oh no, you add up over here. 아빠 잘하세요. 어, 오빠 먹었어. 응? 오빠 맛있어. 뭐? 오빠 있다고. 오빠 나왔어? 네가? 아, 아니 안 먹어. 아, 오빠 갔어? 네가 온다고? 응. 오케이. 그래, 네가 온다는 거. Okay, I'm making a video now, so see you later. So, I'm about to do something real quick. So, over here, where was I? So we have our total, oh, it's not working again. Total 1/2 mv square, which is gotten by these big V's over here. And you can see that's the external energy in the whole thing, external. And then the small things over here, the small over here, it's gonna be added up over here, which gives you this version. That showcases over here this final form. Where's the final form? Over here. But as you can see, where's it? This mu can be written like this because let me think. What's it? You simplify m, and then there's a division somewhere. Yeah, I remember okay over here because m over here is m. So over here is m e plus mp. So divided by m e mpv. That makes sense. This is mu, and that's how you get this internal energy form over here. And this internal energy form, we're not going to care about the external energy, as I said before, and we're going to claim this version over here where we have because this is like the mass over here, we can transform with mv square. It's not really that difficult, but it's the same thing. I mean, it's difficult, but it's the same thing. So over here, you have this formula finally. It's not really anything special. It's just manipulating with orbital mechanics and um, Dr. Becker's and Dr. Rosegreen's different ideas in orbital mechanics and fluid mechanics and figuring them out and just mushing. But we only care about the internal energy for now, actually forever. And then we get this final form over here. And because we're talking about hydrogen, we are going to spherical coordinates. This form, just switch it up. I know how to derive it a long time ago. I don't really care anymore. Just derive it up. Oh, fun fact, when we changed it over here to Laplacian, well, energy is a scalar, so a Laplacian, if you do a double derivative over here or something, because we have a double derivative, analogy for energy, you don't have to even guess. It's always going to be a Laplacian, or you need something like this. You need something like this to happen or something with energy. So one of those two will happen. In this case, it was a Laplacian, like a scalar. If you went to index notation, that would have been more clear, but your choice to do that or not. There's space for index notation. It's always wonderful to do it. But there's sometimes time you don't want to do it. It's your choice. Like in spherical coordinates, you never want to do index notation. I don't think I've never seen anyone use spherical coordinates in index notation. I know what it is. I've seen it actually. No, people do it before. It's just really interesting. We separate. This is a classic 105 and Dr. Becker separation thing. Over here, we have another separation because we have another separation. In reality, you could have separated way easier than this, than the way this does it. You could have done R, Y, no. You could have done R theta and then phi and separated three variables, got a few constants here and there. But yeah, yeah. But here's a little thing you need to know. You're gonna have to realize that you have to add physics here. There's no way to mathematically figure out that this is true. So for example, this is from physics. This is less from physics. That one is just an M. But what I mean by that is later on, if you look over here, no, not look over here. This is not over here. Where is it? The meaning of these things is basically the rotation. So it's M state, so it's M1 rotation, and this is like whatever, it's just some other rotation thing. But it's kind of like that, and you can see what I mean later on. And did I write that down, or did I never write that down? Oh, it doesn't matter if you write it down. I don't think. Well, here it is. L tells the total angular momentum magnitude. M tells how much the angular magnitude is chosen in the z direction, basically. And you can see over here is kind of N is the one state and the S state. Oh, shit, I didn't talk about what it means. In the periodic table, there's 1s, 1p, 2s, 1p, one, so on and so forth. So that's the energy level desiccating. And the match that just comes from physics, and you're inputting it here basically. You're not really solving for them. I don't think there's a mathematical way. I found no mathematical way for you to show that off, but maybe there is, and I haven't searched hard enough. Well, I'm not going to waste more time on this because I have like a whole book to read, and I've only read 4 pages of it because of how dense it is. It's really not that dense. I'm just making it more dense because I need validation on all these stuff, which is pretty bad. So I'm going to actually go faster now, which is good for me because I need to stop validating everything. All right, where was that? You do Lagrange polynomials here, associate the Lagrange, get Y shape over here, and so far, so far. You get this form, with this being what do you call it? This is like a correction factor. Because what happened over here is basically we look at infinity because there's a solution you can solve for, and we looked at near zero because there's a solution you can solve for. But there's no real solution for in between, so yet. But using a possible solution like this, we can plug it back into the original ODE and then solve that one for C. And then we figure out that it's actually a power series over here, which is a pain in the ass, but this only works because the hydrogen is over here. And we get this form over here. And it only works because it's the first state and it's hydrogen. If it's not hydrogen, then you're out of luck. Which is why we see over here a bunch of things. And finally, we get this form over here for n equal 1. And if you increase n, you get a different division factor. So if n is increased, then it's 200 over here. So 200. And then that would be a power En over here, energy factor. Definitely. So it's just there's a probability density over here, but you don't really know that. That's how hydrogen works. And now that kind of makes sense where everything came from now. Because if the book used this notation over here, where E is energy, and then alpha is N, L, and M, and then over here we proceed to see that this is kind of like the notation of Q. Q is kind of like the weight of each individual thing. So you see, and this is for this over here. So what does that kind of mean? So define one weight as this, and you sum all those up, level 1, level 2, level 3, level 4, level 5, level 6, level 7. There's no such thing, although there's a certain level, amount of energy because it is chemistry, and the periodic table is finite. It's not infinite. Let's be clear here. There's no such thing as infinite. I mean, there is infinity, but in this case, there's no such thing. I mean, there could be, your choice. Avogadro's number, if you assume that thing, but whatever, it doesn't really matter. It's going to be denoted as a cursive A in this book, and in this case, first of all, we have done this, which is just a derivative of this case, which is ln, so Q in the bottom, and then derivative here gives you this form. So this is kind of statement. But A is this thing. That's the same thing as Hamel's number, if you're wondering. And where's the other one? Oh, here it is. Uh, why is there? Oh, well, this should have been one slide. But there's U and there's P. And how you get these, I actually do know how to get these. They're a little tricky. There's not in the textbook, but I need to get the other pages up. So if we get dA equal negative S dt minus P dV, you see over here, I believe if you keep the volume constant, you can say something like S equal dA dt or something. And that's how you kind of solve for these stuff. Like, and then you integrate it and get this stuff. Basically, that's how they did it. There's a bunch of them you did. I'm pretty sure this one is oh wait. Did they I think it was U or something. They did something like that. They did a bunch of that. And solve for it basically. I think because or I don't know which one they solved for first, actually. That's what I'm trying to figure out. But there's the first one they solved for, and they solved the rest of it. It's kind of how they did it. And yeah, but that's not the point of this video. This point of this video is to teach you one thing. The book is smart, and sometimes you just have to assume that it's correct and move on, and not waste 3 days on trying to figure it out, and eventually waste a bunch of time learning something that someone else already have discovered. So, moral of the story, don't do what I did.